first Thursday session of Open Readings 2019. And my name is Kastita Zubovas, and it's a pleasure for me to introduce our first guest speaker, Dame Jocelyn Bell Burnell from Oxford University, who is obviously most famous as the person who discovered pulsars and has been active in various areas of astrophysics and as well as outreach activities over the years. And today she'll give us a presentation of transient astronomy.
Thank you very much. Still not, yes, that's working. Good. Thank you very much for the opportunity to be here, and thank you for being here early in the morning. This is one of the new branches of astronomy, and I am very excited about it. So I want to tell you some of the things that are becoming apparent when we move into a new domain. Yeah. That is not working. I need to switch it on. Yep. And still it doesn't work. Ah, connected, yes. Thank you. Hooray, right. So, for example, in the past, the Hubble telescope, Hubble Space Telescope, would take magnificent photographs, very long exposures. This one was a total of 143 hours. 143 hours. It was a very tiny area, equivalent to a tennis ball held 100 meters away. But because of this long exposure, seeing probably the deepest we've ever seen into the universe. And people are very excited about this photograph of a tiny patch of sky. It does seem to be typical, which is good. One of the most important things is there's still black sky between the galaxies, even when you look this deep into space. It is nearly all galaxies. That's a star. You can see the diffraction spikes on it. And I think there's one other star somewhere else. But everything else is galaxies. And these spikes are produced inside the telescope. The secondary mirror is held in place by 4 spikes, called a spider. And it's those spikes that give the diffraction cross on a point source image. But it's a very, very long exposure. And it does mean that although you see very interesting things, you see very, very deep into space, anything that changes, either because it flares or because it moves, gets blurred out and you don't see it properly. And now the situation has changed and we're able to study these things much better. It's a bit like the change from still photographs to movies. It's a comparable change. You can see things that move, you can see things that change brightness. And we suddenly realize there are a lot of things in the sky that change brightness. There's a number of things that move, but a lot of things that change brightness on a quite short time scale. We've known about some of these. We've known about pulsars. X-ray and gamma-ray astronomers have been alert to the time dimension, but optical astronomers have not, and radio astronomers rarely have. And what's happening is that a lot of older telescopes, like the famous Palomar telescope, or one of the Schmidts in Australia, have been repurposed, and there are 1 or 2 new telescopes, like this one in Hawaii, which is called Pan-STARRS. The US got money for that, for talking about killer asteroids, things that move. And they got the US sufficiently anxious about killer asteroids that they got money for a telescope specifically to look for things that move. But it will also do things that change in brightness, things that flare and die. And there have been developments in computing which have helped enormously. The kind of thing that we're now quite often finding is we have here 2 photographs, and you'll be aware that professional astronomers work with negative photographs. So the stars are black and the sky is almost white, grayish white. 2 photographs of the same field, actually taken with the same telescope about 1 month apart. And you can recognize that pair and that little cluster and that little trio as that pair and that little cluster and that trio. But here, there's a new source just to the left of where I have the pointer. And it's appeared within a month, whatever it is. And the idea now is, at least with some telescopes or some observing programs, is to take a sequence of photographs of the same patch of sky. There's argument about the best pattern for this sequence of photographs. It's called the cadence. And the kind of thing you might do is you might take, for example, 4 30-second exposures, 10 minutes apart, and then you go and do another field, another bit of the sky, or lots more bits of the sky. You come back after 28 days. Why 28 days? Because the moon is at the same phase, so you've got the same ambient brightness. So come back when the moon is the same, and take another 4 30-second exposures 10 minutes apart. And again after 28 days. And look for changes. And what's very important is if you find something that's changed, you announce it very quickly so that other astronomers with other telescopes at other wavelengths can do some follow-up and help ascertain what this extra thing is. For example, there's one whole survey called the Catalina Real-Time Transient Survey. It's got 3 telescopes, 2 in the USA, 1 in Australia. And they're actually quite small telescopes. The telescopes that we're building now have 30-meter diameter mirrors, that kind of thing. That's the next generation. So these are tiny, old telescopes, which have been repurposed. 1.5 meters, 0.7 meters, and 50 centimeters aperture. And between these 3, they look at the 3/4 of the full sky, and they've been running for over 10 years. And in that period, they've found 17,000 transient things. The things are mostly active galactic nuclei, external galaxies, things like quasars, with massive black holes in their cores. Massive meaning maybe 10 to the 9 solar masses, that size of black hole in the core. Supernovae explosions, stars usually mass about 10, 20 times the mass of our sun, which explode catastrophically at the end of their lives. And other variable stars that were initially called and still called cataclysmic variables. But they keep doing it, so they're not cataclysmic. They've got enough oomph left to repeatedly burst or flare. And there's a map of all these events. Now, the Milky Way runs through here, and the Milky Way is a sufficiently crowded area that there's no point in looking for transients there. There will be transients there, you will see them, but because it's such a crowded field, you won't be able to say which star it is. So you're not going to make a lot of progress. You're better focusing on areas away from the plane of the Milky Way where the density of stars is lower. So they've neglected that area. This little bit is not visible to those telescopes, and this little bit is not visible to those telescopes. But they've got a lot of red objects, which are these exploding stars. The blue are the not cataclysmic variables. They'll be largely, these will be in our galaxy, these will be largely in our galaxy. The active galactic nuclei in green, and magenta other. And you've probably already seen this pattern. Magentas. This is the plane of the solar system, the planets around the sun. It comes out this funny shape because of this projection, but it is actually a plane on the sky. And although they say they've taken out all the things that they see that move, there's clearly quite a lot of stuff still left here. And my hunch is it's things that actually do move, but they haven't observed them long enough to see that they're moving, so they're not classified as moving, so they're still in this picture. But more and more of them will get taken out. And there's a lot of things going on. Another example is on the famous Mount Palomar, where an old telescope was used for a Palomar survey. It's just fairly recently been upgraded, started February last year. It'll do a whole sky scan in 3 days. It's going to find about 10 to the 4 explosive transients per year. But interestingly, it's generating 4 terabytes of data every night. After 3 years, they reckon they'll have a database of 3 petabytes. And one of the things that's now rapidly developing is machine learning, computer learning. Something pops up over there. And the machine says, okay, I look at a catalogue. Is there anything there? Is there maybe an external galaxy? Is there a star? Is there nothing? And depending on what the catalogues tell you, and also what the characteristics of this flare are, the machine will do some classification. It's a supernova, right, down that pipeline. It's a cataclysmic variable. It's this, it's that, it's something else. And I'll introduce you to lots of different kinds of transients in a moment. But more and more, we are dependent on machine learning. And this is one of the very big new developments in the field. And I would say it has some way to go yet. It's still very new. But there's so much data, you can't do it by hand. And sometimes you can't even keep the data. The computer analyzes it and says, yep, 3 transients, one of those, one of those, one of those, chuck the rest. Which is a little alarming, but I think that's got to be the way it is. So, after that general introduction, some specific types of transients. And the first one is called microlensing. And the little picture in the corner is an Einstein cross. This is the image that you will see for an object like that. If there are massive bodies around, you get this cross shape. And it is related to lensing and relativity. Oops. So, sorry, this is not showing very well in the light. We have an Earth here, not to scale. We have a star that we're looking at, and another star comes between us and it. The stars do all move slowly, but move relative to each other. So that can well happen. And this intervening star has gravity, and its gravitational effect will bend some rays of light, which should have missed the Earth, somewhat exaggerated this slide, to make them bend to the Earth. And similarly, rays of light that should have missed the Earth get bent and back to the Earth. So temporarily, while this alignment is good, we're seeing more light from this star than we normally see. The star appears to have brightened, to have flared. So once again, star that we're looking at, intervening star, and this is the kind of brightening that we see. If the intervening star has a planet, the planet can also cause a little bit of brightening. And so in addition to the main star's brightening, we get an extra blip due to this star, this planet. If the planet's further away from the star, we can get the brightening and then the planetary one. What it turns out is that you sometimes get this without the star. There is a planet with no parent star. An orphan planet, poor little thing, or sometimes called a rogue planet or a free-floating planet. They've now found about 15 of these, and these were totally unexpected. Presumably what has happened, there's been a star with a planet, and another star has come by and ripped apart the star and the planet. So each have gone their own way independently. And so we're seeing this free-floating planet. Gamma ray astronomers have been aware for a while of transient events, but there's a lovely story around this which I must tell you. It goes back to about 1963 or something, 68, something like that. There was a test ban treaty signed between the USA and the USSR for no nuclear tests in the Earth's atmosphere. The USA decided they had to monitor to make sure that the USSR was keeping to this treaty. And the way they monitored was to look for a gamma ray burst, which happened just as you do a nuclear bomb test in the Earth's atmosphere. So they put up some really very small, very primitive satellites called the Vela satellites. They arranged that there would be at least 2 and preferably 3 satellites operating at any one time, so that, if one satellite saw something down there, and another satellite saw something and said it was down there, and preferably a third one saying, yeah, it's down there, then you've got a fix on where these gamma rays are coming from and where the bomb test is taking place. So they always had several satellites up at a time. And they started finding bursts of gamma rays. But they didn't come from over the Soviet Union. They didn't come from the Earth at all. They came from the sky. So they were nothing to do with nuclear bomb tests. They were discovered by accident by these satellites looking for bomb tests. Yes, it was started in 1967. And it took them a long time to get this information declassified. But 6 years later, in 1973, they were allowed to publish the bursts that they had found. And this is typically one of them. And you can see there's plenty of signal to noise. It's seconds along the bottom. So you see they don't last very long. But while they last, they're really bright and sharp. And so small primitive satellites could pick them up. So what is it? It comes from the sky, somewhere, something. Oops. Great debate as to what these things were. Let me just go back one more. Yep, right. So they started plotting them on an old sky map. The Milky Way, again, is along here. And the color is the strength of the burst. And it's random. There's no focus to the Milky Way. They are equally all over the sky. And because they don't show any focus on the Milky Way, it could mean that they're very, very distant and nothing to do with the Milky Way. Or it could mean that they are extremely close and we only see the very, very close ones. So we don't see the concentration to the Milky Way. And the debate raged and the debate ranged. Turns out that there are 2 kinds of these bursts. When you plot the duration, you see that there's one histogram here of short bursts and another histogram here of long bursts, with a break point at about 2 seconds. And I'm going to treat the short and the long separately from here on, because they're quite different things. The long bursts, the ones that are longer than 2 seconds, seem to come from a massive exploding star. A very high mass star that when it's done all its nuclear fusion and ended up with iron in the core, there's no more fusion it can do. Iron is the pits. And it collapses. And in that collapse, maybe makes a neutron star, maybe makes a quark star or a black hole, and somehow produces a very narrow burst of gamma rays. And if the narrow burst of gamma rays, is pointing towards us, we see a gamma ray burst. It was a long time before they managed to pin this down, but there was one particular long burst where they managed to get a position for it. And this is the photograph taken with an extra object compared with an earlier photograph actually done on a different telescope, so the background, the noise is different. But you can see the pattern of sources. It's about where the tip of the arrow is. Something there has brightened up along with this gamma ray burst. And it turns out it's in a galaxy, so it's way, way beyond the Milky Way. So that's why there's no concentration to the Milky Way. And they reckon that for these long bursts, there should be a few per galaxy per million years. So there's typically one gamma ray burst a day these days. It's the kind of rate we have. I'll come back to the short bursts in a little bit. One other kind of thing we've learned to recognize is called a tidal disruption event. Sorry, I'm having trouble with this clicker. So there's a black hole here, which you can't see. There's a star coming on a trajectory that's dangerously close to the black hole. And as the star gets closer to the black hole, tidal effects, gradient of gravity, stretches it out into a cigar shape. And then it breaks up into a number of discrete bits, which in turn fall into the black hole. And with each piece falling in, you might get some flares. A string of optical flares, a string of gamma ray flares, X-ray flares, or radio flares. And they're beginning to find these now. It tends to be the black holes that lie in the centers of galaxies that are the ones that best do this. So we're seeing flashes from near the centers of galaxies. I'm going to say a bit more about transient radio waves because this is where a lot of the excitement is. You know that light can be dispersed with a prism, raindrop, things like that, into its constituent colors. It's perhaps less well known that a radio wave can also be dispersed into its constituent frequencies or wavelengths. And in this kind of case, no, maybe I won't go there for a moment. So you can get the radio wave dispersed. The change in refractive index is caused by free electrons. And this was first discovered by people who studied the Earth and the radio noise that there is in the Earth's magnetosphere, basically. What was happening was there would be a lightning strike on the other side of the Earth. That produces a short burst of radio waves, which then propagate round following the magnetic field lines to us here with our radio receiver. But as it propagates around, it goes past free electrons, and that causes dispersion. So what started as arrives as a descending note, which people called a whistler. Surprise, surprise. And this is the kind of pattern that you get. This is frequency, low to high. This is time, and this is the descending whistle. Now, this one doesn't descend. So it's not been past many free electrons, so it's local. It comes from a lab next door, probably. Similarly, this one, it does not whistle. It doesn't descend like that. It's straight. So that is also locally generated interference. And I'm stressing that because it leads into the next bit of the story, which actually concerns pulsars, these rotating neutron stars which spin around and give a sequence of pulses. They're out in space, they're out in the galaxy. And the pulses get dispersed as they travel through space from the pulsar to the Earth. And so what the pulsar astronomer is picking up is whew, 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 whew. And it's useful because what you don't want to pick up if you're a pulsar astronomer is the pulse generator in the lab next door. Could be confusing. So pulsar astronomers always look for this dispersion, this effect, because it separates out the distant pulsar signal from local interference. Right. So here's a bit of a pulsar, one pulse. Can you just see the descending plot, frequency against time? Here's a rather clearer one, frequency against time. And furthermore, pulsar astronomers can use how rapidly this descends to get the distance. Because if there are lots of free electrons between the pulsar and us, it's... But if it's a nearby pulsar, it's... So looking at the rate of descent gives you the number of free electrons and an estimate of the distance. So one day, a pulsar astronomer was doing his work, came across this lovely pulse, very, very good signal to noise, and here's this descending trace. The snag is, when you start to work out how many electrons there are in the line of sight to that pulse, turns out they're huge, which gives a big, big problem. We're used to pulsars being in our galaxy. We're used to working out how far away they are. But this one, you start counting electrons. So, okay, it's out in that direction through the galaxy, so I start notching up the electrons as I work towards the edge of the galaxy. Let's say the edge of the galaxy is by the projector, and I'm counting electrons that I need to give that dispersion. And I reach the edge of the galaxy, and I'm seriously short of electrons. I've only got maybe 20% of the electrons I need. Where are the other 80% of the electrons? And the snag is, once I reach the edge of the galaxy, the electron density drops hugely. So having gone right across the galaxy in the direction of this burst, I then have to go zillions of miles, zillions of kilometers beyond to get all the necessary electrons to explain that dispersion. These things, and we now know of quite a lot of them, these things are way, way beyond our galaxy, seriously far beyond our galaxy. And yet, while they're on, they're very, very strong. This is the current hot topic in astrophysics, as far as I'm concerned. One of life's little mysteries, really, really intriguing things. The next question was, did anybody else see anything when that pulse was on? Well, you need to get a little bit organized. We've now got multi-wavelength watching, and it's not been wildly successful, I have to say. There's been one case where they've seen something in the optical at the same time. Nothing in the X-ray, nothing in the infrared, nothing in the gamma ray. And there's a lack of information, except for these flipping radio bursts, pulses, which keep happening. So here's several of them. They're all pretty clear. Over 300 have now been seen. 200 of them contributed by one telescope alone. The very large dispersion means they're way beyond our galaxy at considerable redshift. 7 of them have been seen to repeat. Maybe they all do and we just weren't looking, or maybe we've got 2 different categories. At the moment, we don't know. But a little cautionary tale about a microwave oven. There's a radio telescope in Australia, the Parkes Radio Telescope. And on site, they have a staff canteen. And the staff canteen had a microwave oven. Now, they had checked out this oven. You know, they had had it running, and there was no sign of any radio emission leaking out. But they started spotting at this radio telescope some very similar but not quite identical radio bursts. And they all seemed to be the same distance, but they were all over the sky. And they weren't making much progress with it until a graduate student, bless them, made a plot of the occurrence of these bursts against local time. Not something a radio astronomer usually does. And there was a peak between 12 noon and 1 p.m. It's the microwave oven in the staff canteen. Now listen up, because this affects your health. Some people were stopping the microwave oven by opening the door. If you stop a microwave oven by opening the door, there is a short burst of microwaves gets out before it switches off. And you are microwaving your chest. Don't do it. Press the stop button, please. They no longer have microwave ovens on that site. People just could not be trusted to operate them the official way. So the staff are cross, but they solved that one. But lovely little piece of research, even if it wasn't astronomy. And we're still left with the question about what these things are. There are some new telescopes coming along. In particular, there's this new one in Canada, in the Rocky Mountains. You can't see it terribly well in this slide, but this is it again. It's 1, 2, 3, 4 troughs. It's looking straight up, but they can phase it this way. It works at rather lower frequencies than some of the other ones, which is useful, and it's finding stacks of these radio bursts. It's found now several hundred. It's not very good at positioning them because of the nature of the telescope, and it's not very good at pinning down the frequencies because they've got funny bandwidth, but they're still basically commissioning it. So this is sort of preliminary results before they've fully understood the telescope. But clearly, this is going to deliver a lot of information about these radio bursts when it's properly commissioned. In the Optical, a new large, very large telescope building in Chile called the LSST. It's specifically designed to look for transient events. Not that big, 8.4 meter diameter. There's a person, there's another person, so you can see the diameter of the mirror. Start observing planned in 2023. It's got a huge camera with 3 billion pixels in the camera, and the camera itself is as large as a small car. And you may or may not want to go and work on this one. It's expected to have 10 million time domain alerts each night. It's expected to find 10 million transient flaring optical events each night. So there's going to be a huge amount of data, and this field is really, really going to boom. It'll also catalogue 6 million solar system bodies. So that's every tiny rock that there is in the solar system. And about 37 billion stars and galaxies. The data quantity out of this is huge. And this is one of the other new areas in astrophysics, how you handle this quantity of data. There's that much every night, night after night after night, except when it's cloudy. But it's not very cloudy in Chile. So if there's anybody here interested in machine learning, think about this as a future direction. Then there's a very large radio telescope being built, half of it in Australia and half of it in South Africa. It's called the Square Kilometre Array. because between those two sites, it will have a square kilometre of collecting area, of telescope area, operating in the radio. The slide is of a little bit of it of Australia. It's called ASCAP, the Australian Square Kilometre Array Pathfinder. And there's also one in South Africa that's just about getting working. The South Africans had a radio telescope called the Karoo Array Telescope, KAT. Have we any Dutch speakers here? Nope. The Dutch for more is meer. Meerkat, more of the Karoo Array Telescope. So they're enlarging the Karoo Array Telescope. And they're doing something very, very sensible that we should have thought of long ago. Alongside the Meerkat radio telescope, they've got Meer Licht, more light, an optical telescope slaved to the radio telescope. So wherever the radio telescope points, the optical telescope also points, and it has the same field of view. So if the radio telescope picks up a transient, a burst or something, the optical astronomers will be able to say, yep, we saw something at the same spot at the same time, or we saw something at the same spot, but before or after. So that was going to be really, really useful for pinning down some of these transient events. And the final kind of transient event that I want to talk about is gravitational radiation. Are you aware that gravitational waves have been picked up for the first time in the last few years? Predicted by Einstein. Very, very hard work to detect, but they have now at last picked them up. This is a Wikipedia movie. It's meant to represent a pair of stars in here orbiting each other, and as they orbit, they send out these gravitational waves in the fabric of space. The two stars will gradually spiral in because these waves carry away energy, and having spiraled in, they will probably merge. These waves travel out at the speed of light from this pair of stars, but they're quite hard to detect. The interesting thing is, here's a pair of stars. It's an uneven pair, which is fair enough. They're orbiting, they're sending out gravitational waves, and they're gradually getting closer. And as they get closer, they're going around faster, the orbit's shorter, and so they're sending out more gravitational waves, so they're losing more energy, so they're moving closer even faster, and sending out even more gravitational waves and moving closer, and ultimately merge. And the pattern of gravitational waves that you expect from an orbiting pair of anything is that it starts off nice little even wave, but gradually the period's getting shorter and the amplitude's getting greater, and then they merge. And if you were to listen to this, it's a rising frequency. It's a chirp. Whew. And the way they've done it, excuse me, is with a Michelson interferometer. They've got Michelson interferometer with very long arms. The arms would be several kilometers long. It is otherwise a basic Michelson interferometer. The mirrors at the ends of the arms are quite massive, and it's those masses that the gravitational wave moves. Gravitational wave is not dipolar, it's quadrupolar. And so this Michelson interferometer shape is very appropriate. So by quadrupolar, it means it's doing this, the oscillation. And so I don't think I can align my arms with the interferometer very well, but you get the idea. So the mirrors at the end move, the fringes move. Again, it's technically very, very difficult. The movement that they were detecting was of the order of 10 to the minus 18 of a meter. comparable to the size of an electron or a quark. The technology that went into their interferometers was amazing, is amazing. They're shut down just at the moment for an upgrade to improve the performance, but one of the great achievements of our lifetime is the detection of gravitational radiation, gravitational waves, and the opening up of a whole new spectrum. Now, the kind of thing they're picking up at the moment are the dramatic big events where there's a burst of stronger gravitational waves. They have seen the merger of two neutron stars, but what they're really picking up are the mergers of pairs of massive black holes, 10, 20, 30 times the mass of our sun. And we did not know such black holes existed until they started picking up this gravitational radiation. So it's technically fantastic, and whilst I was pretty certain they would detect it at some point, I wasn't sure I'd be here to see it, so that's really, really good. Yeah. So this is the actual signal from the first detection. Two interferometers. The interferometers are angled different ways, which is useful because it helps discrimination against noise. And one of them is shown in the navy blue and one of them in the brown. And out here, they're really doing nothing, but here they begin to align. Greater intensity, higher frequency, greater intensity, higher frequency. This is the merger, and then this is the aftermath. And it's only taking a fraction of a second. And these were these rather surprising 30 solar mass black holes at 1 billion light years away. So quite distant. And with one of these mergers, they've got some information at other wavelengths as well, which is really, really nice. And been able to add a lot to what's going on. So what we think is happening is that there's a pair of objects, it might be stars, but probably black holes, orbiting each other, begin to spiral in on each other, and eventually collide. And as they collide, there's probably a torus and some jets. So it has to be aligned the right way for us to see it. If the jets go off at some other angle, we probably don't see anything here on Earth. But one of the gamma ray bursts was one of the gravitational wave bursts was accompanied by a weak gamma ray burst. And that must have been one where it was pointing at us. And these are short gamma ray bursts associated with these mergers. So, time domain astronomy is to me the most exciting bit of astrophysics at the moment, with stacks of amazing new results rolling in, lots of them unexpected. A lot of what I've talked about is very, very new, a lot more research needed, but it's a bit preliminary. But clearly there's lots and lots going on. So I'm hugely excited about this, and I hope I've communicated some of the excitement and amazement to you. And thank you for your interest.
Thank you very much for this exciting talk, and we have some time for your questions. So, who would like to begin? There.
Thanks for interesting lecture. My question is, in this lecture, the event of tidal disruption of a star in the vicinity of black hole was mentioned, and my question is, I know that the nearest star that orbit supermassive black hole in the galaxy center around a stable orbit is S2 star, and has the event of tidal disruption of certain star on more small distance to the galaxy center been observed or not really?
Yes, there are lots of stars orbiting the black hole in the center of the galaxy. And in fact, there is a lovely video that you can find online showing stars. I sometimes use it with schools because it's a brilliant display of Kepler's laws. The star orbit slowly goes zoop, zoop, zoop. So, but none of those are tidally disrupting, at least not yet. The orbit must gradually decay, and presumably one day some of them will fall into the black hole in the center of our galaxy. It's in the centers of other galaxies that they suspect they've seen some tidal disruption. Sorry, one only? I'm not sure, certainly in other galaxies. I think there may have been some in the Milky Way, but the stars on the video have not yet fallen into the black hole. They are far enough away. Yeah.
Okay.
Hello, thank you for your lecture, and I would like to ask if you know at which rate are the gamma-ray bursts found from the new and coming transients, and what is the likelihood of the transient astronomy as being the future way to discover gravitational waves?
The gravitational wave surveys go on all the time, except when they are upgrading the equipment, which they are doing now. But the gravitational wave detectors just run and run and run. And there are these two big ones and one and maybe some more in the future. And they look for coincidences. Sorry, I've lost the first part of your question.
Okay,
We'll come back.
In the meantime, we'll take another question.
Thanks for an excellent lecture. I want to ask a more general question about the status of astronomy, astrophysics. Mm-hmm. So if we look at Earth, at our Earth, so we evolved and life evolved and then humans appeared and then a lot of things happening now, social events, wars and so on, that were not ingrained in the creation, but they are nevertheless interesting. So talking about space, talking about astronomy, what's the fraction of interesting, fundamental, unanswered questions in astronomy related to the creation, to the origin of the universe? And what is the fraction of interesting and unanswered questions related to whatever happened afterwards? How everything that was created lives? So how you would distinguish? Are there interesting questions about what happens afterwards, how these stars and planets interact and so on. So where the focus of astronomy is now?
There are many foci now. There's a lot of astronomy done, and different groups have got different foci. So, for example, one of the very new areas, along with Transient, is concerned with exoplanets, planets round other stars. Those are all stars in our own galaxy, but there's a lot of work there. They are finding thousands of planets round other stars. Indeed, if you look at the night sky, you should say to yourself, I can see 5,000 stars, but there are more planets up there than there are stars. So there's a big area there. There's big areas concerned with the origin of the universe as a whole. That's another huge area of study. And really between the different groups in various places, almost the whole swathe is covered, but it tends to be physical rather than biological, and it's physics rather than ethics, which is interesting that that's the way we work. But with all the new planets being discovered, there is a lot of work on, not by astrophysicists, but more by astrobiologists, on how life might arise in these planets and how we might tell whether there was life on these planets or not. And then there are the ethical questions. If we really believe there is life on that planet, do we talk to them? Do we not talk to them? Do we aim to go kill them? Etc.
Okay, any more questions?
You've remembered, sorry. Right, yes. Gamma ray bursts, we are beginning to understand. And we can see the link between short gamma ray bursts and gravitational wave bursts on the basis of one event. So it's slightly perilous, but in one occasion we have an unambiguous link between a short gamma ray burst and a gravitational wave burst from the merger of two neutron stars. Yeah, that's really about as far as we've got. It's very much work that is going on, work that causes quite a lot of excitement. Every so often there's a new piece of news which goes round very fast. So a lot of people are beginning to watch transient events in general because there seems to be so much potential for new understanding there, and a lot of excitement and a lot of fun.
Thank you for the lecture. I have a question about neutron stars. Generally, neutrons, when they are free, their lifetime is really short, approximately 15 minutes. But how can, and the neutron stars are included by the neutrons mainly, and how they survive so long time? My question is about this. The neutron stars.
Neutron stars are rich in neutrons, but they are not just neutrons. They have amazing, amazing density. You have, can I get the numbers right? The radius of the star is 10 kilometers, and it has the same mass as the sun, which is 10 to the power 24 tons. It's like taking a thimble, a sewing thimble, and putting 7 billion people into the thimble. It's that dense on average, but there's big range of density. They seem to be quite stable. Great discussion going on about what exactly they are made of. In particular, the physics, you know, from a very dense center out to a rather dense outside. What particles are there? There's more than neutrons. There's a lot more than neutrons. They are very, very extreme physics. They are extreme density, extreme magnetic field, extreme electric field, extreme gravity, extreme rotation. The physics is hard, very hard. So the answer you get a little bit depends who you talk to at the moment.
Okay, I think this wraps up the time we had for questions. So let's thank our speaker again.
Thank you very much.
And in a few minutes, we start with the first student presentation session on astronomy and theoretical physics. So I'll ask the students to come along and put their presentations on the laptop. And enjoy the rest of the conference, everyone.